Yeah, welcome. So the topic we'll be discussing in this lecture is planning. So this is the next topic with what we have discussed in the last class. With that, we'll stop discussing inference in first order logic. With this, we'll be moving to the next topic, which is planning. So basically, in this topic, we'll be discussing like how to construct a complex plan, how to construct a complex plan of action. So here the agent will take the advantage of the structure of the problem. Based on the structure of the problem, how to construct a plan for moving from an initial state to the goal state. Okay. So it is the task of coming with a sequence of actions that will achieve a goal is called as planning. So this is how we define planning. The the task of identifying the sequence of actions that will achieve a goal, right? And also here we'll be using some special languages which are quite expressive. So we'll be using some languages which are more expressive for representing plans, uh, actions, and states. Okay. So far we have discussed only about propositional logic and first order logic, but we'll be discussing some special languages which are more expressive than first order logic, right? So it is something like mm, so if you see propositional logic or first order logic, they are very generic, but these languages are something like domain specific languages. It is specially designed for certain domains. Okay, hence it is more expressive than first order logic or propositional logic. So in this chapter for planning, we'll be considering only environments that are fully observable, deterministic, finite, static, and discrete. So these are called as classical planning environments. So we'll be considering only the environment which is fully observable. That is, the agent will be able to see the full environment. The deterministic, that is the next state is only decided by the agent's current action, since it is called as deterministic. And it is finite. The number of actions that can be done were finite. It is static. That is the agent. That is the environment will not change when the agent is deliberating. And it is discrete. It is not a continuous environment, it is discrete environment. So we consider only this type of environment. On in these environment, how planning works. That's what we are going to discuss. So such environment. So when you discuss planning on these environment, that is called as classical planning. Whereas if we discuss planning on partially observable and stochastic environment, planning on such environment is called as non-classical planning. But so we'll not be discussing about non-classical planning here. We'll be discussing only about classical planning. So if you consider in the original starting lectures, we have discussed search problems. Especially we have discussed heuristic search techniques. So that is also one form of planning. For example, we have discussed we have discussed Escher algorithm. We have also discussed depth first search. Depth first search is not a heuristic search technique. It is an informed search technique. But they are also one form of planning. But there the agent can be overwhelmed with irrelevant actions, and also there will be we are trying to, and, and it is very difficult to find a good heuristic function. So if you recall, for to solve the problem using Escher algorithm, first you have to find a good heuristic function. So actually your heuristic function is going to control the performance of the algorithm, right? If you find a good heuristic function, then then it is of high probability that you will get a good solution, right? But actually finding a good heuristic function is difficult. So these are some of the challenges which we faced mm, uh, in normal search problems, right? And also those problems, and also these problems where we have in the search problems cannot be decomposed. They cannot be divided into several small problems and then you cannot solve, because the algorithm is of different nature. But here, but coming to planning, here we have a language that is expressive enough to describe a wide variety of problems, okay, but restrictive enough to allow efficient algorithms to operate over it. So, so here we'll be so in this section we'll be discussing some planning using a language known as stripes. So there are many languages, but here we'll be discussing one or two languages. So one such language is called as stripes. So using this language, we'll be discussing like how planning can be done. We'll be taking some example problems, and 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 what are the sequence of steps required to reach the goal state, and how that steps can be represented using stripes. That's what we are going to discuss. Okay, fine. So before that, let us understand some preliminaries. So basically these planning problems, they decompose the problem into several small problems. They decompose the world, that is the domain. The world here in the sense domain, that is the problem is restricted to a particular domain. So that it decomposes the world into logical conditions and represent a state as a conjunction of positive literals. So it decomposes the world into several logical conditions and represent a state as a conjunction of positive literals. For example, if you consider the proportional literal poor and unknown, it might represent a state of an agent, which means that some individual is poor and unknown. So, so normally states are represented like this in, okay. So normally states are represented like this using stripes, poor and unknown. And also you can also use first order literals for representing states. For example, at plane 1 comma Melbourne and at plane 2 comma Sydney, which means that plane 1 is at Melbourne and plane 2 is at Sydney. So you may use this type of sentence, this type of statements in case of an package delivery problem. So this is similar to first order logic. But the thing is here you cannot use any variable. You can use only ground term. Actually, this is an example for stripes, but it is similar to, this statement is similar to FOL statement. Whereas this statement is similar to a proportional logic, but with conjunction. Okay. So the state can be represented either something like this, or it can be represented like this. Right. So when you represent like in proportional style, it is like a conjunction of several literals. When you use FOL style, it is something like this. But here you should not use any variables, only we have to use ground term. All these are ground terms. So so the literals, so as it was mentioned, the literals in the first order state description must be ground. That is, you have to use only ground term. You cannot use functions. I mean, you cannot use any variables, and also it should be function free. You cannot use function. So if you, so a literal like this is invalid. This is invalid. You cannot use at x comma y, because x is a variable and y is a variable, right? So you can say that at plane 3 comma New York, that is okay, because these two are ground terms. Plane 3 is a ground term, New York is a ground term, right? So in the first order description, you can use ground term directly, but you are not supposed to use variable. Similarly, functions are not allowed. So this is not allowed. At father of Fred comma Sydney is not allowed, because this is a function. Father of Fred is a Sydney. Sorry, father of Fred is a function. Hence, this type of statements are not allowed. And also, stripes uses a closed world assumption. What is meant by a closed world assumption? A closed world assumption is one where the unmentioned statements are assumed to be false. If a statement is not mentioned, then it is assumed to be false. Okay. For example, you are not mentioning about any statement. Uh, say, say, say what example I can say. Uh, yeah. For example, See, if you are saying that at plane 3 comma New York, it means that it obviously means that plane 2 is not in Sydney. Sorry, plane 3 is not in Sydney. So you need not mention that not at plane 3 comma Sydney. Like that, you need not mention this type of statement is not required, because when you don't mention something, which means it is false, right? So that's what it means. So meaning that a condition that is not mentioned in a state are assumed to be false. Say for example, initially let us assume plane 3 is at Sydney. Okay. So initially say at one point in time, at time t naught, plane 3 is in Sydney. That is true. Plane 3 is in Sydney. Okay. But later, say at time t4, that plane has gone to New York. So now to the knowledge base, we will add one statement at plane 3 comma New York. Like that we will add. But at the same time, we will remove this. When you remove this, it means what? Plane 3 is not in Sydney. So that's what this statement says. Any condition that are not mentioned in a state are assumed to be false. If something is not mentioned, then it is assumed to be false. So these are some of the properties, or these are some of the features of the language stripes. So here we'll be using the language strips for representing the planning problem. Right. And what is a goal? A goal is a partially specified state represented as a conjunction of positive literals. So if there is a statement, a goal is a partially specified state represented as a conjunction of positive ground literals. So for example, if there is a statement like this, rich and famous are at P2, Tahiti. Okay. A proportional state yes satisfies a goal yes satisfies a goal G if S contains all of the atoms in G. Okay. So what does it mean? A proportional statement yes satisfies a goal G if S contains all of the atoms in G. For example, let us assume this is our yes. Say this is yes. Yes is rich. Okay, here that example is there. Let us take this example. Here we have an example. This is rich and famous and miserable. This is one statement. Yes. Okay. And say that our goal is to identify someone who is rich and miserable. So now say this is some person P1, and the person P1 is rich and famous and miserable, and your objective is to find someone rich and miserable. So this is our yes and this is our G. So what is the rule says? A proportional state yes satisfies a goal G if S contains all of the atoms in G. So you have to check whether S has all of the atoms in G. So G contains rich. Does S also contains rich? Yes. G contains miserable. Does S also contains miserable? Yes. So this is a goal state. Okay. Say for example, you are asked to identify someone who is rich. Then also this will be a goal state. Okay. So it is not required that all these things should be satisfied. In goal, whatever is there, that should come here. Okay. So you are asked to find someone who is rich and miserable. Yeah, that is what this. You are asked to find, say, someone who is rich and famous. Then also this satisfies that. Okay. So you are asked to find someone who is rich and unfamous. Someone who is rich and unfamous. Then this one does not satisfy, because this person is rich but he is famous. But you want rich and unfamous, right? So this is how we check for goal state. Okay. Fine. And how we represent action. So all these things we are discussing for the language stripes. Okay. An action is specified in terms of precondition that must hold before it can be executed. So before executing an action, some precondition is to be satisfied. If that preconditions are true, then that action can be applied. Once you apply that action, some result will happen, right? Say for example, consider this action of flying a plane from one location to another location. So this is the action you want to do. This action, what is the action? Fly the plane P from the location from to the location 2. This is what the action is supposed to do. Fly the plane P from the location from to the location 2. Okay. But for this, there is a precondition. What is the precondition? The plane P should be at from location, at P comma from. Before you apply this action, all these things should be satisfied. What are the things? This particular plane should be at the location from, and P should be a plane at P comma from. That is, P should be at the location from, and P should be a plane, and from should be an airport, and to should be an airport. So if these conditions are satisfied, then this action can be applied. That's what it says. Okay. So if this precondition is satisfied, then you can apply this action. Once you apply this action, what will be the effect? Effect will be this. That plane will move to 2 location. So at P comma 2 and not at P comma from. So no more P is at from. Right. So this is for our understanding. We are representing like this. But as we have mentioned in the knowledge base, we will only add what? At P comma 2. And previously, whatever is there at P comma from, previously initially the knowledge base contains at P comma from, that will be just removed from the knowledge base. Once you remove from the knowledge base, if something is not mentioned, it is false. It means that the plane is not at from, at location from. Currently the plane is at location 2. Right. So this is how we apply action. When you apply action, you have to check the precondition. If the precondition is satisfied, then apply the action. For goal state, all the literals mentioned in the goal state should be available in the statement yes, then goal is achievable, right? And how we represent things in stripes, we can use a proportional logic style where we use conjunction of literals, or we can use first order logic style. But when you use first order logic style, you are not supposed to use any variables. You should use only ground terms. And also we are not supposed to use any functions. Functions are not allowed. And stripes follows a closed world assumption. A closed world assumption is one where unmentioned states are considered to be false. Okay, fine. So this is more properly called as an action schema. Okay, so whatever we are representing here, this is called as action schema. The action is otherwise called as action schema. To improve the reliability, some planning schemes divide the effect into the add list for positive and delete list for negative literals. Okay. So for more clarity, the negative literals you can put in a list which is called as add list. So you can have two lists. One is add list, the other one is delete list. All the positive literals will be moved to add list, which means that contains currently the knowledge base contains those statements at P comma T naught, whatever the other things also. So all the negative literals will be moved to delete list at not at P comma from, which means currently these are not in knowledge base. Only these are whatever in the add list will be treated as something in the knowledge base. The things in the delete list are not in the knowledge base. So here is an example for planning at P1 comma JFK. It means the object P1 is at location JFK. At P2 comma SFO, the object P2 is at location SFO. Plane of P1. P1 is a plane of P2. P2 is also a plane and airport of JFK. Okay. JFK is an airport and airport of SFO. SFO is also airport. So it means what? P1 is at JFK, P2 is at SFO. P1 is a plane and P2 is a plane, and JFK is an airport and SFO is a airport. Right. So here the precondition to apply this, yeah. So this satisfies the precondition. What precondition? P is at F, P is at location from, and P is a plane, and from is a airport, and to is a airport. So these preconditions were satisfied. So it means now the planes can fly. Two planes. For two planes, it is satisfied. For plane 1 also it is satisfied. For plane 1, its from location is JFK. For plane 2, its from location is SFO. Now both this plane can fly and it can reach their destination. Okay. So starting in state yes, the result of executing an action A in state yes, that is same as yes, expect that, except that any positive literal P in the effect. Starting in state yes, result of executing an applicable action A is a state yes that is same as yes. This is except. Okay. Except that any positive literal P in the effect. So what does it mean? It says that, see, currently you are in some state yes. And from this state, if you apply an action A, you will get a state, you will get a state S dash. You will get a state S dash. So what is S dash? S dash is nothing but same as yes. It is nothing but same as yes plus some positive literal. It may add some positive literal to yes. Are you getting? Because you are finally reaching some destination, based on that some positive literal can be added. So that is what it says. So it may add some positive literal to S dash, and also any negative literal, negate P is removed from S dash, right? So both the things will happen. Yes, that is true. So S dash is what? S dash is nothing but yes, plus it may add some positive literal uh, to to yes, and also it may remove some negative literals from yes. Okay. So this is something like a definition, because when you currently you are in a state yes, and when you apply an action yes, action A, the resultant will be S dash. Now what is this S dash? S dash is same as yes. With the new state, when you move on to the new state, some positive literals may be added and something can be removed from yes. Some negative literals may be removed from yes. That's what it says. Okay. Right. So let us consider this example at P1 comma yeah. Okay. So here, thus this is an example. Thus, after fly P1 comma JFK comma SFO, so we are applying only this rule. This is the initial case. This is the initial scenario. This is the initial scenario. Now say that you are applying only this rule. Fly P1 comma JFK comma SFO. You are performing this action. That is, you are asking the plane P1 to fly from JFK to SFO. Are you getting? Initially, plane P1 is in JFK. Now you are asking the plane P1 to fly from JFK to SFO. So after executing this action, what will happen? After executing this action, what will happen? At one new rule will be added. One new literal will be added. That is at P1 comma SFO. P1 will come into now SFO. And this will become negation. This will become negative. No more P1 is in JFK. So positive should be added. So P1 comma SFO will be added and this negative thing will be removed. So P1 is at SFO. Now P2 is also at SFO. P1 is a plane. P2 is a plane, right? And SFO is a airport. Now we need not talk about JFK, because there is nothing in JFK, right? There is no object in JFK, so you need not talk about JFK. Hence, this is the or if you keep JFK also, no issue. There is nothing wrong in keeping JFK, because as per our original statement, we have JFK. So that is not going to impact our result. But after flying, what happens? This becomes positive and this becomes negative. So we add this and we remove this. So this is the result you are getting. At P1 comma SFO, P2 comma SFO, P1 is a plane, P2 is a plane, JFK is airport, and SFO is airport. Right? So this is an example for this. That is, when you are starting at a particular state, if you apply an action, you will reach S dash. Now what is this S dash? S dash is nothing but same as yes plus adding some positive literal and removing some negative literal. So here we are doing that. This positive literal is added and the negative literal not at p1 comma jfk, that is removed. Okay. So similar to similar to stripes, there is another language which is called as ADL, which is more expressive than stripes. So stripes is insufficiently expressive for some real domains. It is not sufficiently expressive in case of some real domain. As a result, we have many language variants. We have many different languages for planning problems. One such example is called as ADL, Action Description Language. In ADL, the fly action could be written like this: action fly p plane. Okay, so here we are creating something like a variable or an object. For the plane, we are creating an object p. P is a plane. From is an airport. Okay, so from is an instance of an airport. To is also an instance of an airport. So here this is the action fly p from to, that is fly the plane p from this location to this location. Now before performing this action, as usual, the precondition should be satisfied. What is the precondition? The plane p should be at the location from, and from should not be equal to 2. If from is equal to 2, then there is no point in flying, right? There are two preconditions. P should be at location from, and from should not be equal to 2. And what is the effect? So if this precondition is satisfied, then you can apply this action. If you apply this action, what is the effect? After applying this action, P will be at location 2 and P is not at location from. No more P is at location from, right? So this will be the effect. So this is how we represent in ADL. Whereas in stripes, we represent directly fly P comma from comma 2, something like that. So these are some of the differences between the stripes and ADL. Stripes allow only positive literals, something like this, poor and unknown. Stripes does not allow negative literals. Actually, it won't allow any negative literal. Okay. Whereas ADL allows both positive and negative literals. You can include statements like not rich and not famous. And stripes uses closed world assumption. It is all unmentioned literals are assumed to be false. Whereas ADL uses open world assumption. That is, unmentioned literals are unknown. If some literals are unmentioned, then it means that we just don't know about that. It's not that they are false. Are you getting? Effect of P and not Q in case of stripes. So as you know, stripe does not have any negative literal. So if there is something we want to do like this P and not Q, it means we add P and remove Q, because stripe, it will not allow the negative literal itself. So whenever you want to do something like this P and not Q, it means P will be added to the knowledge base and Q will be deleted. That's the meaning. Whereas in case of ADL, P and not Q means it will add P and not Q. P also will be added, not Q also will be added. And not P will be deleted, Q will be deleted. Its opposite things will be deleted. So if P is true, then obviously not P is false, right? So not P will be deleted. If not Q is true, then obviously Q is false. So Q will be deleted. Like that it works. Whereas in case of stripes, if something is negated, then that will not be in the database. And it includes only ground literals, rich and famous, something like that, right? So this is positive literals. First rule is positive literals. This is ground. You cannot include any variable in stripes. Whereas ADL can include variables. It can also include quantifier. There exists x such that at p1 comma x and at p2 comma x, like that it can include variables, and also it can include quantifiers. And goals or conjunctions in stripes. Okay. Whereas ADL allows conjunction and disjunction. Stripes does not allow disjunction. It allows only conjunction. Whereas in ADL, you can have conjunction and also disjunction. Not poor and famous or spot. Like that, it can include. Okay, negation also it can include. Effects are also conjunction in stripes. Whereas ADL can have conditional effects. When E means E is an effect only when P is satisfied. So So that is this effect E will be true only if P is true. So based on some condition, this will happen. Like that, you can mention in ADL, but such options are not available in stripes. Okay. So you can see that ADL is more expressive than stripes. That's what we are trying to say here. And stripes does not support equality operation. Right? You cannot compare two things whether they are equal or not. Whereas ADL supports equality operation. And stripes does not support any data types. Whereas ADL can support types. So here we have used like P colon plane, which means P is a type of plane. Right? So this is the difference between ADL and stripes. There is also another language called PDDL, Planning Domain Definition Language. So which is more expressive than ADL and stripes. PDDL includes using PDDL. You can also represent things in the style of stripes and ADL. So PDDL includes sub languages for stripes and ADL. That is, it can also provide an environment, something like a stripes and ADL. But stripes and ADL are adequate for many real domain problems, right? So we may face some problem with stripes and ADL. So for most of the problems, stripes and ADL is enough, but we may face some restrictions with stripes and ADL when we encounter ramification problem or qualification problem. So what is a ramification problem? So this is how the ramification problem is defined. If there are people, packages, and dust modes in the airplane, then they too change their location when the plane flies. So, so in the stripes, in the previous example, we have discussed like fly, okay, fly P, comma, from comma to. So which means the plane is flying from this location to this location. It's not only the plane is flying, right? Along with the plane, people are also flying, right? Whatever the things in the plane also flying. So how will you represent that? That problem is called as ramification problem. So actually everybody is flying. It's not only the plane is flying. All the passengers in the plane, all the things they were carrying, everything is moving to some other location. So we don't have that much expressive power to represent all those things using stripes and ADL. That is called as ramification problem. Okay. And what is qualification problem? The problem of unrepresented circumstances that could cause an action to fail. So it is not that. So initially you may think that a particular action will always work, right? But under some condition, an action may not work. Initially you might not have thought of that, and hence you might not have programmed that. But that may happen in the real world. So probably the stripes or ADL may not be able to capture such circumstances. Okay, so these are some of the drawbacks with what you call with ADL and stripes. That is, these drawbacks are called as ramification problem and qualification problem. Ramification means along with the people, packages, and dust modes, all other things were also fly, but you cannot represent everything that flies along with the plane. That becomes too complex. Similarly, qualification problem means normally mm, we set some conditions for applying a what you call for see for applying any action. There is a precondition, but some of the precondition we might have left out. So it's not that every precondition you could have included. See, so of course we try our level best to include all the preconditions, but but in the real world scenario you don't know what will happen, right? So 90% of the time, whatever the preconditions you give, or even 99% of the time, it will work. But sometimes, as you might have missed out some preconditions, sometimes you may not be applied to, may not it may not be possible for you to apply certain rule. So that is called as qualification problem. So here is an example using uh, using, I think this is using using stripes. Let us discuss this example. Okay, so this is an example based on air cargo. This is the initial situation at C1 comma SF. The object C1 is at SF. That is what it means. And at C2 comma JFK, the object C2 is at JFK. Okay, and P1 comma s at P1 comma SFO. The object P1 is at SFO, and P2 comma JFK. The object P2 is at JFK, and cargo of C1, which means C1 is a cargo. C1 is some cargo. Cargo means something, what you call, some load which you want to transfer through flight. And cargo of C2. C2 is also a cargo. And plane of P1. P1 is a plane, and plane of P2. P2 is also a plane. And airport of JFK. JFK is an airport. And airport of SFO, which means SFO is also an airport. So these are initial conditions. That is initially in the airport. There is an airport JFK, and there is another airport SFO. Okay, and there is a plane P1. The plane P1 is at airport SFO, and there is another plane P2 which is at airport JFK, and there is a cargo C1 which is at airport SFO, and there is a cargo C2 which is at airport JFK, right? So this is the initial situation of the problem. Now what is our goal? This is the goal at C1 comma JFK and at C2 comma SFO. Initially, if you see, cargo C1 is at airport SFO and cargo C2 is at airport JFK. But our goal should be the reverse. Cargo C1 should go to JFK and cargo C2 should go to SFO. Okay, so this is our goal. So first, what should we do? There are several steps here. Remember properly. Understand the. So first, we should have the clarity of the problem. So there are two airports. What are the airports? There are two airports. One is SFO and the other one is JFK. The cargo C1 is at SFO. The plane P1 is at SFO. The cargo C2 is at JFK. The plane P2 is at JFK. Okay. Now this cargo should move to here. What is the goal state? This is our goal state. SFO JFK. Cargo C2 should be in SFO and cargo C1 should be in JFK. That is the goal. So if you want to do that, then what should happen? First, this cargo should be loaded into this plane. C1 should be loaded into plane P1. C2 should be loaded into plane P2. Okay. And P1 should fly from SFO to JFK. Right. Then P1 will come here. And P2 should fly from P1 should fly from SFO to JFK. And P2 should fly from JFK to SFO so that P2 will come here. Now the plane has reached here. Again here cargo should be unloaded. So the cargo C1 will be unloaded here. This is unload. Similarly, the cargo C2 will be unloaded here. Okay. Whereas here the cargo is loaded. This is load. This is load. So these are the operations. First you have to load the cargo. Okay. Then fly the plane. Then unload the cargo. So what is the first action we are doing? Load C comma P comma A. Right. That is load the cargo to the plane P at the airport A. Okay. Load the cargo C in the plane P at airport A. For that, what is the precondition? The cargo should be at the airport A and P should be at the airport A, right? That is C should be at airport A and P should be at A. And C should be a cargo, P should be a plane, and A should be an airport. So this is the precondition. This is the precondition. If this precondition is satisfied, then you can apply that rule. Okay. So if this precondition is satisfied, this rule can be applied. And if you apply this rule, what will be the effect? The effect is no more the cargo is at P. Sorry, no more the cargo is at A, right? No more the cargo is at A. Now the cargo will be in P. P is plane. So you are just loading to the plane. Now what happens? Not at C comma A and in C comma P. That is, cargo is not in the airport A, but cargo is in the plane P. Right? Okay, fine. So this is the first rule. So this is the first rule we want to apply. After reaching the destination, we have to unload. Okay. After reaching the destination, we have to unload. Unload C comma P comma A. Unload C, the cargo, from the plane P to the airport A. For this, what should be the precondition? The cargo C should be on the plane. Okay, the plane P should be at A, and C should be a cargo, P should be a plane, A should be an airport. If these conditions were satisfied, then you can apply this unload operation. When you apply the unload operation, what will happen? C will be no more at C will be no more. C will be at A. After applying unload, C will be in the airport, and it will be not in the plane. Right? Okay. See, these are rules. This is another rule. Now there is another rule which is fly. Fly P comma from comma 2. That is, fly the plane P should fly from this location to this location. For that, what is the precondition? The plane P should be at from location, and P should be a plane. So this statement just says that the object P should be at location from, and P should be a plane, and from should be airport, and 2 also should be airport. 2 is here. So if these preconditions are satisfied, then what will happen? After applying this rule at P comma 2, so P will be at location 2 and not at P comma from. P is not in from. So P is not at location from. This is the third rule. So these are the 3 rules. Okay. Now this is just the rule. This is not the actual action path. Now what action you have to do? That we have to find out. We have these rules available. Now this is our initial state. If you want to reach to this goal state, what action we should do? First we should load. Load what? Load C comma P comma A. So here which C? C1 comma P. To which plane? To P1. C1 comma P1. In which airport? SFO. Okay. That is, the cargo 1 is loaded to the plane P1 in the airport SFO. Right? Similarly, in the other airport also we should load. What is that? Load C2. The cargo C2 should be loaded to the plane P2 in the airport JFK. So after applying this operation, C1 is in the plane P1, and after applying this operation, cargo C2 is in the plane P2. Now what operation we should apply? Fly what? Fly P comma from comma 2. That is P1. Fly P1 from where? From SFO to JFK. After applying this operation, P1 will reach JFK. Right? Similarly, fly P2. Fly P2 JFK comma SFO. After performing this operation, JFK will reach SFO. Right? Then what we should do? Unload. Okay, finally we should do unload. Now unload C comma P comma A. So unload what? Uh, Unload now the cargo C1 has reached where? Cargo C1 is in JFK. Okay, cargo C1 is in JFK and cargo C2 is in SFO. Right? So what should we do? Unload C1 comma P1 comma JFK, because plane 1 is currently in JFK. Right? Similarly, we should write what? Unload C2 from P2 in the airport SFO. So this is the rule. So 1, 2, 3, 4, 5, 6. This rule, 6 rules will take us to the destination. Okay. So this, yeah. Here unload they have not written, but unload also you should include, right? So load C1 comma P1 comma SF4, fly P1 comma SF4 comma JFK, load C2 comma P2 comma JFK, fly P2 comma JFK comma SF4. But later you should also unload, right? Yeah. So only if you unload, they it will come into that particular place, right? So you can also include unload. Unload unload C1 comma P1 comma JFK. Now P1 has come to JFK. This is our goal. C1 should be in JFK, right? So now C1 has come to JFK. Similarly, unload C2 comma P2 comma SFO. Now C2 has reached SFO, right? So this is the solution. This is the solution. These operations will lead to the solution. So this is the plan. This is the plan. Now, if you want an AI program to do this, the AI program should find a plan like this. So this plan is at one level of abstraction. So that's what we are telling. It's not capturing everything. It's only targeting about the plane and the cargo. So as we already discussed, along with the plane, people also move. All those things, it's not capturing. So it all we cannot provide a full-fledged solution for everything. So we are targeting what you call we are providing some solutions for some targeted tasks. Okay, so so that's it. So we'll continue discussing about planning, but for this session we'll stop here. So thank you.